So in this session, we are specifically interested in format of analog signals. And for that, we can say that to transform an analog waveform into a form that is compatible with digital communication. So we outline the steps in which our analog signal can be converted to a digital signal. And specifically, we would be needing sampling, quantization and encoding, and baseband transmission. So we would be discussing sampling first. So what is sampling? In sampling, we convert continuous time analog signals to discrete time analog signals. So sampling is the first step in analog to digital conversion. Note that the output is still analog, it's not digital. So it finds some applications in specific areas such as periodically monitoring the temperature in a given locality, that is measuring a data at appropriately spaced intervals. In sampling theory, the most important phenomena is that it is a reversible process, provided that some conditions are met. So these conditions are outlined in this theorem. So it says that a real valued band limited signal. So by band limited, we mean that its spectrum is not until infinity, but it is until some values, say W or 2W. So it says that a real valued band limited signal having no significant spectral components above a frequency of W Hz is determined uniquely by its values at uniform intervals spaced no greater than, this is the sampling time Ts, which is equal to 1 over Fs. Fs is the sampling frequency, so the Fs must be equivalent to 2W if the original message signal was RW. So by this, what we mean is that if we have a signal whose spectrum is simply like this, so the sampling frequency Fs would be equal to 2W. So if this condition is met, so this would mean that if we have an input x of t and we pass it through a sampler and we get x, let me call it x bar of t. So if this condition is met, we can recover back our x of t. So this is the intuition for sampling theorem. So just as a repetition, that if you have a signal which is band limited to W, so the sampling frequency must be equivalent to or greater than 2W, so that you can recover back from your sampled signal to the original signal. An important point that I have highlighted is significant spectral component. By this, what I mean is that if we have a time domain signal, say simply a rec function, and if we take the Fourier transform of it, so this would be a sinc function. But you know that the sinc function is decaying with respect to frequency f, but there are still some content, so it would converge to 0 at infinity. So the bandwidth would be infinity, but the majority content or the majority power is until the first or main lobe, right? So you don't have to consider W to be at infinity, but rather you can just look into the significant content and that should be sufficient. So for reconstruction, the first and foremost is that you must satisfy this condition, that is the Nyquist criterion. Next, what we would do is we would use a low pass filter to recover back our original signal. So I would discuss this next as well. Just to give a pictorial view of the sampling theory, let us consider that we have a signal g of t. This is continuous time signal. So we pass it through a multiplier and we also pass a sampling pulse train, that is delta ts of t. This is an impulse train, and at the output we will get g of t multiplied by the impulse train, so we'll get g delta of t, right? So consider that you have g of t which is band limited to W Hz. So in time domain, say this is our signal waveform for g of t, and similarly the sampling pulse train, that is delta ts of t, is having unit amplitude and samples occurring at interval of ts seconds. So this means that we have this impulse train. So this means that we have this impulse trains which have a constant amplitude of 1 and the sampling period is also constant. Now when you multiply g of t, this signal, with the sampling pulse train, so you have a sampled waveform which is simply the multiplication of signal waveform for a given sampling pulse train. That is, at this point it is going to pick a sample, similarly at the second point it is going to pick a sample, and so on. So you would have this sampling pulse train. So the Nyquist criteria says that the time period ts, this time period should be less than or equal to 1 over 2w, right? W is the bandwidth of our message signal or the signal waveform g of t. So what will happen if you change the sampling period ts? So if you are changing this duration ts, so let us first consider that we are dividing the sampling time by 2, that is ts nu is equal to ts by 2. So by this what I mean is that between this, now again we have one more delta function in between the zero value and the first sample. So for that we would have a sampled waveform which has more number of samples. But if we increase the sampling time ts, we would have less number of samples, and if we continue to increase, we will get less and less samples. Now let us look into some of the mathematical aspects of sampling theory. Consider that this is our signal g of t. For simplicity, we consider that the spectrum has a triangular shape. So if we sample our g of t, so we would have g delta of t, that is at constant intervals ts we would pick values and which are represented over here, g delta of t, right? So this g delta of t is nothing but g of t times the impulse train delta t minus nts given over here. So this is the time domain expression for our sampled signal g delta of t. Now if we take the Fourier transform of this, we know that for g of t we would have g of f, it is multiplying with this summation. So if in time it is multiplying, in frequency domain it would be convolving. So if you have a delta function in time and if you take the Fourier transform, again you would have a delta function in the frequency domain, and moreover you would have a coefficient 1 by ts. So this block has a Fourier transform expressed over here. So in this equality we know that if there is a function g of f and you multiply it with a direct delta function, so this function would be shifted to the delta function. This is something that is done over here, that is the g of f is now shifted as per this delta function, where 1 over ts, that is the sampling time ts, is converted to sampling frequency fs over here. So what this function means is that if we have a triangular function having this spectrum g of f starting from minus w to, and terminating at w, so this means that this function g of f would have m copies and each copy would be at mfs, where fs is the sampling frequency. So by Nyquist criteria, let us say that our sampling frequency fs is equal to 2w. So we have all of these copies. This original copy is over here when m is equal to 0. This is the first copy, this is the second copy, and so on. A small concern over here is that we cannot create a delta function. So we would have to look into some alternate means to eventually get here. Alternately, g delta of t is also expressed over here, that is g of t multiplied by the delta function, that is t minus nts. Note that you can also express it in terms of g nts delta t minus nts, where n is from minus infinity to infinity. So this is again coming from the properties of direct delta function. So moving on, as previously mentioned, that this delta function is quite difficult to generate. However, we notice that the delta function is a periodic function, and for periodic function we can use a Fourier series. So this delta function is converted into its uh, respective Fourier series, specifically complex exponential Fourier series, which I have expressed over here. That is, this delta function is now converted to exponential Fourier series, which is exponential j2 pi nfst, right? And you also would have 1 over ts, that is the sampling time period. So how we convert from delta t minus nts to over here, you can have a look on example 2.12 in our textbook. Now again, if we take the Fourier transform of the second expression, we would achieve the third expression, that is fs n minus infinity to infinity gf minus nfs, which is that g of f is available at integer multiples of the sampling frequencies fs, where the integer is appearing over here in the summation block. Note that this expression 3 is also achieved previously over here. Now the most important aspect is regarding the reconstruction of the message signal, and what should be the value of sampling frequency fs over here. Now consider that we have an original signal whose spectrum is expressed over here. Now if we set the sampling frequency less than 2w, the original signal has a bandwidth of w. So if we set the sampling frequency less than 2w, so our fs say would be at 1.5w. So the image station would be interfering with our original spectrum, which is shaded over here. So you're going to lose the information which is over here. This is something that we call as aliasing, and it is nothing but undersampling with respect to the Nyquist criterion. Now if fs is exactly equal to 2w, that is the lower bound, so this means that fs is equal to 2w, right? So its lower side lobe lsb would be at w and upper side lobe would be at 3w, right? Similarly 2fs, which is at 4w, so this image would have lower side lobe at 3w and upper side lobe at 4w. Now herein the image spectrum is not interfering with our original spectrum, and hence we can recover back our original spectrum. So how can we do that? Say this is our original signal and this is the spectrum of our sampled signal. So we have GSF, which is equal to Fs and minus infinity to infinity GF minus NFS. So this expression is plotted in terms of spectrum over here, right? So in order to get back our original signal, what we need is we need an appropriate low pass filter. So by that what I mean is, if you have a low pass filter over here, so you can remove all the images, the image spectrums, and you would recover back your original signal. So from this intuition we can say that g of f is related to g delta of f, such that if you consider minus omega to omega as the frequency range, that is minus omega to omega, and moreover you normalize the 2w factor which is expressed over here. So g of f is equal to 1 over 2w g delta of f, where f is from minus w to w, right? So this is at the output of our low pass filter. So by this we have recovered our original signal by means of a low pass filter, which is expressed over here. So all of this exercise tells us that g of t is uniquely determined by g nts. That is, if you have a continuous time signal, provided that the sampling period ts is following the Nyquist criterion, then you can recover back your original signal, which is g of t. Now let us look further into the reconstruction aspects, that is moving from here to here mathematically. So to reconstruct g of t from g nts, that is the sampled signal, or we can express ts as 1 over 2w, so g n by 2w. So in order to reconstruct g of t from the sampled version, so this can be done by means of the following derivation. So starting with the inverse Fourier transform of the sampled signal, right? G delta of f. So we take the inverse Fourier transform to achieve small g delta of t, right? Whereas we would have exponential j2 pi ft from the inverse Fourier transform, and the integration is from minus infinity to infinity. So we will change the limits of integration as per the Nyquist criterion, which says that the f should be between minus w and w. So by changing the limits of integration from minus infinity to minus w to w as per the Nyquist criterion, we go from g delta of t, the sampled version, to a recovered g of t, right? And the rest of the expression is as is. Also, we know that g delta of f is the Fourier transform of this time domain counterpart, that is small g delta of t. So we can express this in terms of a discrete time uh, Fourier transform DFT, which is done in the third equality. In the fourth equality, we take the summation out while we take the integration inside the summation. The summation has a variable n, so this gn by 2w can be taken out of the integration. Note that the limits of integration is w, but the variable of integration is f, so we can take gn by 2w outside the integration. So we achieve the fourth equality. So solving this integration is quite straightforward. That is, if you have e j theta d theta, you would have 1 over theta e j theta with respect to the limits a b, right? So you can achieve the fifth equality. Lastly, sign of an argument over an argument can be expressed in terms of a sinc function. So in short, from here we can recover back our g of t using all of these steps. Here in this expression 5 is an interpolation formula for g of t. Now some further intuitions. Previously we have discussed that g delta of f has this spectrum. That is the original frequency content and the image frequency contents. So by inducing these limits minus w to w, what we have done is we have simply multiplied this with a rec function, right? This is in frequency domain. So if this is a rec function in frequency domain, so in time domain we would have a sinc function, right? So if you take the inverse Fourier transform, so you would have a sinc function. So that's why you have a sinc function appearing over here. Also note that we have multiplied g delta of f with this filter, low pass filter at zero frequency. So if it is multiplied in the frequency domain, right? So in time domain we would have the convolution, and hence we have this convolution, discrete time convolution. Remember, the discrete time convolution is simply k equal to minus infinity to infinity x of k h of n minus k, right? So you have t minus n. So this is your discrete time convolution. So this means that if sampling is exactly at the Nyquist rate, then we have g of t, which is in terms of the sampled version g nts times the sinc function, right? So sinc function interpolation is also known as infinity order hold. Why is it so? It's because in the frequency domain, as I mentioned, we have simply a rec function, right? So if we take the inverse Fourier transform, we would have a sinc function. But this rec function, which has a sharp transition, it would need an infinity order filter to achieve this transition, right? So that is why we have this infinity order hold. So we would not be able to create this kind of a filter. By that, what we mean is, even though we have sampled at the Nyquist criterion, but still we would lose some information. One way to improve the results is to have sampling frequency much greater than 2W, right? For example, in our telephones, our Y spectrum is bounded to say 2.5 to 3 kilohertz, but cell phones sample our voice at 8 kilohertz. Also note that the, the dots are actually the samples. So at each sample we would have this impulse response. That is, you would have at this sample you would have a sinc function, at this sample again you would have a sinc function, and on all the samples you have a sinc function. Also, from the property of sinc function, since each sample is distant by time period Ts, so this means that if you take this sample, so the zero crossing would be at the next sample, and the next zero crossing would be at the subsequent sample, and so on. So the sinc function would find its zero crossing on this, and on and for all of them. So finally, by this expression, we would achieve back our original signal. So as mentioned, it is theoretically perfect, but it can never be done in practice because it requires samples from the signal for all time. So therefore, real interpolation must make some compromises. Just as a quick note, interpolation is that if you have these two dots, how are you going to connect these two dots? Whether it would be this shape or this shape. So this is interpolation. Hence, for practical scenarios, we could use a first order hold, that is, we have an impulse response rather than a sinc function previously discussed. We have now an impulse response which is triangular, right? So if it is triangular, no, it is time limited, and since it is time limited in frequency domain, we would have a sinc square function which is bandwidth unlimited, right? So if you convolve h1 of t with our sample signal, you would have the outcome which is represented over here by the red curve. The dotted one is the original signal, whereas the g of t is the recovered one. So we're going to lose some information over here. We are not going to get exactly the original information. We also have a zero order hold. It has an impulse response of simply a rec function. So if we have a rec function in time domain, in frequency domain, we have a sinc function. And for that, in time domain, if we convolve h naught of t with the sampled signal, what it is going to do is it would take a sample and it would hold it for some time, and then at the new ts value, it would take a new sample, hold, and onwards. So this is our zero order hold. So in short, we can extract back our original signal completely if we use an infinity order hold, right? But that is not practical because we do not have any impulse response which starts at minus infinity in time and goes to infinity in time. So we make a compromise and we go for first order hold, that is time limited, or a zero order hold which is also time limited, and both of them compromise on the performance. Next is aliasing or undersampling. Previously mentioned that we are going to have image stations, and these image stations are going to cost an effect on our original spectrum. So we are going to lose this information. So if we're going to lose this information, how are we going to rectify this problem? Note that the sampling theorem is for strictly band limited signals. Thus, to avoid aliasing, we may limit the signal bandwidth or have higher sampling rate. So these are the two criterion. While sampling rate, you can set this fs to 2w or more, so that would avoid this aliasing. Also, you can pre-process the original spectrum, a thing that I'm going to present next. So let us discuss how we can improve the performance of a recovered signal which is impaired by aliasing or undersampling. Consider that we have a signal g of t which has spectrum given over here. We first pass it through an anti-aliasing filter. So what this filter does is it chops off this section which is going to be interfered. So in our this signal, it is going to chop off over here the spectrum restricted until here and here. Next, when the original signal passes through this filter, we would have the spectrum in which the sidebands have been processed. We utilize the multiplier that includes the sampling pulse train to eventually get the sampled signal at the output, right? So if you're using the anti-aliasing filter, instead of getting impairment or interference until this point, no, the interference will be only until the edge over here. It will not be until here. So we're going to save over here, but we would still lose this information, but the overall performance would be improved. To prove this point, let us look into an aliasing example of 2D images. On the right side, we have an image in which the anti-aliasing filter is not implemented. Over here, you can see these wave patterns that are appearing in this image. While if we use the anti-aliasing filter, we can get rid of this pattern as seen on the picture on left, which uses the anti-aliasing filter. Similarly, assuming a sinusoidal signal which is having a frequency of 1800 Hz, and we sample the signal at 2000 Hz. That is, the blue one is the original signal and the red one is recreated based on the interpolation. Note that the frequency of the signal is 1800 Hz. So this means that the sampling frequency according to the Nyquist criteria should at least be 3600 Hz. But we have set the sampling frequency less than that, that is at 2000 Hz. So we would not recover the original signal, and in fact we will get a signal which has a much lower frequency. In fact, we can estimate the frequency of the recovered signal. So considering that our sampling frequency is 2000 Hz, we know that this sampling frequency is based on the Nyquist criteria, which states that the original signal should be around 1 kilohertz. So for a signal whose maximum significant frequency is at 1000 Hz, would desire a sampling frequency of 2000 Hz. But right now the blue signal is at 1800 Hz, right? So we have a difference of 800, right? So based on this folding frequency, if you subtract 800 from 1000, you would have around 200 Hz, which is the frequency of the red signal. Aliasing is also apparent in a fast moving wheel of a vehicle. For example, if you see a wheel, you mark a position and visualize it. So even though the vehicle is moving from left to right, but you would see that this point is now appearing over here, and next over here, and next over here. So while the vehicle is moving in this direction, the wheel would appear to be moving in the opposite direction. This is also an effect of aliasing. The following content was useful in the making of this video. Thank you.